Papua, Indonesia, a vast and remote region of the world, the western half of the island of New Guinea. With its impenetrable jungles and towering mountain ranges, it is one of the most diverse and challenging environments in the world. At its uppermost elevations, Papua is home to some of the only glaciers in the equatorial region of the Pacific Warm Pool. It is here that a group of scientists from the United States, Russia, Italy, Australia, and Indonesia have gathered to set out on a mission to study these last surviving ice fields. This international team consists of glaciologists, geologists, and meteorologists. Their aim is to drill and retrieve ice cores from Papua's rapidly retreating glaciers in order to preserve the climate history stored in the ice.
I'm a glaciologist. Been a professor at Ohio State now for over 30 years. In that period of time, we've run 56 expeditions, 16 different countries, looking for the history of climate as it's recorded in glaciers around the world. To do what we do requires a special team of people who are willing to work at high elevations around the world.
When I first started out in this academic endeavor, I just viewed glaciers as an interesting geophysical phenomenon. They're just beautiful, interesting, naturally occurring phenomena.
The main reason that we want to be here is to answer various questions about climate and how and why it changes through time.
Ice can record many past environmental processes, including climate.
In the ice and glaciers, we have a very original composition of moisture from atmosphere and whatever trapped, which could be solids like a dust, terrestrial dust, cosmic dust as well.
When I started to look more closely at what glaciers really were, you realize that they're really extraordinary things. They're part of a very complex hydrologic cycle. They tell us something about the Earth's climate system, and they are responding very much to a global climate trend, both in the past and what we see now.
This is actually the second part of a two-part drilling program. Last summer we drilled in the Cordillera Blanca on Wakan, where we drilled the deepest cores recovered to date, 195 meters from the Andes. And that is on one side of the Walker Oscillation in the Pacific Ocean. And now, this year, we're on the opposite side. And these two records, even though we're talking about thousands of miles of separation, should be related through this very large global weather phenomenon.
The Walker Oscillation is a weather phenomenon that occurs in the lower atmosphere. It consists of a high-pressure system over the eastern Pacific and a low-pressure system over the western Pacific. When the Walker Oscillation weakens, it causes warmer water temperatures in the eastern Pacific, and an El Niño occurs. When it reverses and the waters in the western Pacific are warmer, a La Niña occurs. Records of this phenomenon are recorded both in the glaciers in the Cordillera Blanca in Peru and the glaciers near Puncak, Jaya in Papua, Indonesia. This is just one of the many past climate records the team hopes to recover from Indonesia's glaciers.
Not all glaciers are created equal. We don't just go and drill any glacier. There are morphological differences in the glaciers. Glaciers can reflect very local events which we don't want. And glaciers like these, for example, sit very high on mountaintops, and so they are recording more, certainly a very regional picture. You know, we hope that we would be able to tie in that very broad regional picture with the global picture, because we know climate change is not uniform. Not all places are treated equally. There are winners and there are losers in climate change. So we hope that by looking at the specifics of the regional climate system, we're able to actually connect it in some systematic way with the big closed system of what is the climate structure of that planet.
And once they're gone, they're gone. And that's another problem with the ice history, is that Yeah, it's a history of how the climate system worked long before people were a factor. But once that history melts, then you will never be able to reconstruct it. Maybe the climate may change in the future, it may get colder, and the glaciers may grow, but that growth will start a new clock, and we'll have lost the old clock when they disappear. When they're lost, they're gone forever. And so having that ice, and there are questions, I'm sure there's a lot of things that could be measured on those cores that we aren't currently doing, like the fire history of a place like Papua, or what's the fire history in the Amazon basin before we have any records in the human documentation. Those cores, those glaciers have been recording those variations through time. Here we would expect to see things like the major volcanic eruptions, Tambora in 1815 or Krakatoa in 1883. Those ash layers, sulfate layers from those major eruptions get archived in the layers of snow. And if you can read those and identify the volcano, then you have a timeline.
We're at the Valley Dump and we're unpacking all the core tubes from the core boxes, getting them ready to bring up to the ice camp to put ice core in it. We've had some delays with the drills, but it looks like we have a complete auger drill. As of now, we don't know where the drills are, but they may be in customs or they may be somewhere else in transit. So we're just trying to figure everything out and make do with what we have at this point.
Despite the missing drills, the team continues to prep their equipment in anticipation of their move up to the glaciers. Because of the relatively warm temperatures on the glaciers, freezers must be used to store the ice cores once they are drilled. The team also preps and tests their specialized high-altitude generators that will power the drill and provide electricity for the team while living on the glaciers.
In order to do this project in this part of the world, you have to have logistics, and we're very fortunate to have the support of Freeport and the logistics of being able to get to these sites and ultimately to actually be able to bring the ice core down.
Helicopter support with getting the equipment and the scientists to and from the glacier, and then also perhaps most crucially is transporting the ice cores from the summit of the glacier to freezer storage in Tamika. And without that, it would be incredibly difficult. This is a challenging and technical mountain, and it would be not only difficult but dangerous to transport the ice cores down the actual mountain. And so without this logistic support of Freeport, we would, it would be possible, but it would be incredibly difficult.
Before moving to the glacier, the team must learn to use a method for transporting equipment by helicopter called sling loading. They will use sling loads to receive equipment and send core samples to storage facilities at lower elevations. Although the team will move to the glaciers by helicopter, they must also hike several routes to and from the glaciers through the Marin Valley. In the event of an emergency, these routes will be used to get off the glaciers quickly and safely. The hikes also help the team acclimate to the 16,000-foot altitude at which they will work for several weeks.
There's not a lot of air up there, so everything is just compounded. Everything that you would do at sea level that feels easy requires a lot more effort and concentration at altitude, not just because it's physically more difficult because of the lack of oxygen, but it's also cognitively more difficult. You really need to pay more attention about what you're doing because your brain isn't functioning as it would with all the oxygen you have at sea level. So you really have to pay a lot more attention, and it's a more concerted physical and mental effort.
team also uses this time to study and take samples from the many lakes throughout the Marin Valley. These lakes were formed as a result of the retreating glacier. They test the alkalinity of the water, measure the stable oxygen levels, and the water's isotopic composition.
If you go high enough on any mountain range or in the cold regions, in the polar regions, you can find a history. Every snowfall, every yearly annual accumulation is preserved. And if you can recover that, then you can read the history of the past. If we look at what do we know about our climate of the planet, looking at temperature, we've had instrumental records for maybe 150 years. That's very short in the history of the Earth. And what we try to do is to use the ice archive to read what's the variability in the past. How rapid has climate changed naturally before humans were a player in the climate of the planet. So we try to get that long-term perspective to better understand where we are at the beginning of the 21st century and where we might expect to be 50 years from now. In this part of the world, these are the only glaciers that are in the center of the Pacific warm pool. There should be a history here of El Niños, the monsoon variability for this part of the world. And it's in an area where the glaciers are disappearing. And so it's very important to capture whatever history that they offer before that history actually melts away.
What we're really trying to do here is understand climate change, the patterns of climate change, and the rates of this change. The realities are that this has happened in the past, it'll happen in the future, but at this particular point in time, we've never had to deal with climate change as connected to the population. And maybe, after all, that's what it's all about. Maybe it's not just an interesting intellectual exercise, it has real practical considerations for human occupancy on the planet, where we live, how we live, and all those connected issues with respect to population. The realities are, and it's a very pragmatic, straightforward statement to say that humankind is an agent of geomorphic change and humankind is an agent of climate change. And that those signals and those changes that are brought about by the human occupancy of our planet and our needs and our increasing needs are in effect superimposed on these other changes that we know to be taking place.
For about the last 21 days, we've been waiting for our gear, and for about the last 2 weeks, we've been in Papua, with 1 week down in Tembagapura, and then another week up here at the GBT mess, where we have been reading a lot of books, using the internet occasionally, and going for a couple hikes. And it hasn't been that bad. I mean, the group spirit has been good. The morale's still been high, and we know that things have been moving forward, so that's helped keep our spirits up. But yeah, it's been a little bit tough kind of waiting around, and we're really looking forward to getting up on the ice and getting to work.
After several weeks waiting at Freeport's mine office area for the drills to arrive, they decide to send the team's engineers, Victor and Vladimir, to construct a new drill at Freeport's machine shop in Tamika. At the machine shop, Victor and Vladimir are assisted by Freeport engineers in modifying and building the new drill. Once the modifications are finished and the plans completed, they are sent to the machine shop to be manufactured. Freeport's employees prioritize the project in order to quickly machine the needed parts in 2 days. Before the parts can be completed, the team receives good news. The lost drill parts were found in customs and have finally arrived in Papua. Upon the arrival of the needed drill parts, the team begins to move their 6 tons of equipment to the glaciers.
So finally we are leaving. It's 22 days that we are waiting for this time. We are going on the ice to there. The plan is to install the camp on the ice and to transport all the drilling equipment on the drilling site.
Once the equipment is transported, the rest of the team moves to the glacier. With the team's visas set to expire in the coming weeks, they must move quickly to the glaciers to complete their mission. With all the team members on the ice, they move quickly to build their camp before sunset. With the camp completed, the team takes time to get to know their surroundings and prepare for their first frigid night on the ice. The next day, the team begins setting up the drill and the processing equipment on the peak above their camp.
We started drilling the first ice cap up there, 120 meters below the camp where we are. And so at the beginning things were a little bit slow. The ice for us is relatively warm. This means very close to 0 degrees Celsius. So this makes things a little bit slower. It's much more difficult to drill to cut this ice. But finally, yeah, we believe we have found the recipe to drill this ice. Apparently we have to use water in the borehole, and this really facilitates the process very much. So today we made bedrock at 30 meters of depth, and this is the first of the course that we plan to drill. This glacier is completely out of the ordinary because it's melting from the top to the bottom, and it is by far the glaciers in the worst condition that we have ever drilled. This glacier is melting very fast, and yeah, basically what we drill is just ice. Normally we first drill snow, then fern, and then ice. Here we almost immediately drill the ice from the surface down to the bedrock. Okay, now is the third run. So this is 40. It's fern, and we have ice lenses at 8, 9, 21, 22, and one very large between 30 and 31.5.
Meter by meter, the team catalogs and details each piece of ice core before it goes into the storage freezers. In a turn of events, some members of a local Papuan village begin to protest the drilling operations on the glacier. Although the mission had previously been explained to the local tribal leaders, they claim to have only recently heard of it. They threatened to hike to the glacier and shut down the team's drilling operations. Lonnie and Freeport management meet with the locals in an effort to explain their mission.
So in the Papua, the locals believe that the head of their god is the glaciers. And so there was an issue, okay, here we are as outsiders and we're drilling into these glaciers. And it's like drilling into the skull of God.
and we were stealing, and which is kind of ironic because in a way what we're trying to do is get the memories of the history of the climate from these areas. But in their religion, that's the head of the god, the legs and arms are the mountain ranges that come down. And so we were seen as outsiders coming in. So I think it was very important to meet with them, to present what we do, to explain that we do it all over the world, and the fact that we weren't looking for gold or copper, that we were trying to get the history of climate from that area. So I think that was an important thing to do, and I think at the end of the day we were successful in that they said that they would leave us alone.
With the ice core drilling operations on the glacier coming to a close, the team begins sending the ice core samples to Freeport's cold storage facilities in Tempagapura.
Every place we work, there's a different challenge logistically on how you keep those cores frozen from the time you drill them until you get them to the cold rooms here at Ohio State University. Keeping the ice frozen and cold from the time that it's drilled until it gets to Ohio State, a process that may take a month. There's a lot of challenges on making sure that there's not a breakdown in the logistics and you lose that record along the way. Now, having run 57 expeditions, we have never lost an ice core. We have in the insulated boxes that we use for transporting the ice core a cryopack material, something like a blue ice that we freeze also when we're freezing the ice core, that goes into those insulated boxes, which will give us up to 5 days to find a freezer. So we have a backup in case something goes wrong. We can keep the cores outside of a freezer for up to 5 days.
As a further precaution, Lonnie personally accompanies the ice cores on their journey to help ensure the safe arrival of this precious cargo to the Byrd Polar Research Center. This is key in that the ice cores make several stops in Jakarta to be packaged and x-rayed, exposing the ice cores to Jakarta's tropical heat. From here, they will be sent to the Byrd Polar Research Center located at Ohio State University. Back in Papua, the team dries and packs the massive amount of equipment for its journey back to the Byrd Polar Research Center.
The center was the brainchild of a professor who was here when I was a graduate student, Dr. Goldthwait, who had had several expeditions into Greenland and the polar regions during the 40s and early 50s. And Dr. Goldthwait thought it would be important to have a place where the scientists who worked on collecting that data would come, reduce their data, and publish the results. So he formed the Institute of Polar Studies. After 3 years, it was determined there was quite a bit of interest in cold regions and that the center actually should go on. And so it was the Institute of Polar Studies up until about 1985 when we were approached by the Admiral Byrd family about receiving his archives of all of his expeditions to the North Pole and the South Pole, for which we would change the name of the center to the Byrd Polar Research Center. And of course this year we're celebrating our 50th anniversary, which makes us one of the oldest polar research institutes in the United States.
After several years of planning and anticipation, the arrival of the ice core from Papua marks the end of another successful mission and retrieval of an ice core record. After a 10,000-mile journey, the ice arrives safely at the Byrd Polar Research Center, and the team moves quickly to place the Papuan ice cores into their cold storage facility. They can now begin their study on this key piece of the puzzle to unlocking our planet's past climate history.
So basically, we start the process by planning the cutting of the ice. We'll cut the ice, we will decontaminate the ice by washing the samples in the clean room, and we will analyze the water samples obtained by the melting ice. So basically what we hope to observe is a variation in stable isotopes. This variation will tell us whether or not annual layers are recorded in the New Guinea ice core, because normally during war periods we have enriched isotopes, while in the cold periods we have diminished isotopes. And so we hope first to see this interannual variability, or to see at least different variability, decadal, centennial, or even millennial variability. It is very difficult at the moment to see, to say or to imagine what kind of results we could get, because we don't have an idea of the time period which is spanned by this core. And in this respect, an important quick information that we could get will be from the analysis of the few organic particles that we found entrapped in the ice core. This will be carbon-14 dated, and we'll have a pretty much precise idea of the time covered by these ice cores.
We have over 7,000 meters of core stored at minus 30 degrees C in 2 separate cold rooms. And of course the facility is set up with its own fail-safe system. Each room has an alarm that goes to a central location here at the university, which is manned 24 hours a day. But each room has 2 compressors, and we have a backup natural gas generator and a huge compressor capable of running the whole facility should power fail for any reason.
That machine is a mass spectrometer that measures trace elements and metals in the ice and in general in the water. Being a mass spectrometer, basically he discriminates between one trace element and another. What is exceptional of this machine is that we can analyze metals down to very, very low concentrations. This machine is able to pick up 1 part per trillion of these elements. For other elements, we can pick up 1 part per billion. The trace elements are indicator of past climate and past environmental conditions. And as soon as we find a large enrichment, maybe concomitant with sulfur, this represents an indication that a major volcanic eruption happened in the past, possibly interacting with climate conditions, because the more ash we have in the atmosphere, the less solar radiation is absorbed, and so the climate cools down, at least temporarily.
We're the only group who has a tropical collection of ice cores, because not only do we drill the cores like those in Papua, but we will store at least half of the ice we recovered for the future, because we know that 20 years from now technologies will be much better. There'll be brighter people than we are, but the ice will be gone from these locations. And so we want to preserve some of that for the future.